Hey guys, so in this video we are going to solve this question about power in AC circuits. So you can see here we've got two parallel loads. Load 1 is represented by this box, load 2 is represented by that box, and what I've said is load 1 is 25 ohms, it's an RC circuit, and the power factor is 0.85. Load 2 is 15 ohms. The power factor is 0.6, and it is an RL load. So I'm also asking for you to find the value of R and C for this load right here, and to find the value of R and L for this load here. And then finally, I want to know the apparent power, the true power, and the reactive power for this entire circuit. So in order to get that, we're going to need a little bit more information. I'd like to know what the total impedance is of this entire circuit. That would probably be the fast way to victory over here. And we're going to draw the impedance triangles for each of these loads here. So let's start with that. Okay. So this one right here, we've got a load of 25 ohms and the power factor is 0.85. Well, we know that the power factor, if my pen will write, is cosine of theta, where theta is the angle of the impedance. And that theta is also going to be the angle of the power triangle. So here's theta right here. Okay, so if cosine of theta is equal to 0.85, as it says right here, well, we should be able to find theta then. So in order to figure out what that theta is, we need to use the arc cosine. So arc cosine of 0.85 is going to give us theta. Well, let's see here. (31.78). Okay, so this is an RC circuit, so that's going to be a negative. So it's negative 31.78. It's negative because it's down in the fourth quadrant on the unit circle. Let's do the same thing for this load over here. So this load is in the first quadrant, so its triangle is going to look like this. So this is the RC, and the RL is over here. Once again, I'm going to have to find the angle here. So the power factor is 0.6, so arc cosine of 0.6 is what? It is 53.13 degrees. Okay, so the angle of this triangle is negative 31.78. I'll say it here, negative 31.78. And the angle of this one here is 53.13 degrees. Okay, well, what is Z total for load 1? It looks like it is 25 ohms. So that's the hypotenuse of this triangle right there. It's 25 ohms. And the load 2 has a total impedance Z of 15 ohms. So that's this hypotenuse right here. Okay, so the adjacent here is the resistive portion of that load, and the opposite is the reactive portion. So let's get the adjacent and the opposite for load 1. So to get the adjacent, it's going to be 25 ohms times cosine of 31.78. So 25 ohms cosine of 31.78 is giving me 21.25 ohms. And that is this answer right here, 21.25 ohms. And let's get the other side, the opposite. So we're going to use 25 sine 31.78, not tan, sine. Sorry, I don't have my glasses on. And that is 13.16 ohms. Okay, but that is the capacitive reactance of this capacitor. It's not the actual capacitor value. So if the capacitive reactance is 13.16, that means that, give me 1 second. That means that we need to solve for C. So C is going to be 1 over 2 pi, and what's the frequency? It's 60 times 13.16. Right there. So let's get C. That's going to be 1 divided by 2 pi times 60 hertz times 13.16 ohms, and that is 201.56 microfarads. So 201.56 microfarads. And that's the value of the cap in this circuit. Well, let's look at this load now. We've got to do the same thing over here. So to get the real part of that triangle, that's the resistive part, it's going to be 15 ohms cosine of 53.13. And that is 9 ohms. 9 ohms. All right. And then to get the reactive part, that is what the reactance of the inductor is, it's going to be 15 sine of 53.13, and that is 11.99 ohms. I'm going to call it 12 ohms, just to keep things simple in this example. All right, so the inductive reactance is 12 ohms. What's the formula for inductive reactance? It's L equals 2 pi. It's XL equals 2 pi FL. So L is going to be XL over 2 pi F. So that's going to be 12 divided by 2 pi times 60. Let's see what we get. Sorry for that glare there. 12 divided by 2 pi times 60. And that is 31.83 millihenries. 31.83 millihenries. Great. So we now know all of the components in our RC load and our RL load. Well, now I want to know, what is the power triangle for this entire circuit here? So probably the easiest thing for me to do here, since I really don't feel like calculating this current and then adding them together to find IT so I can do the power calculation, I think what I'm going to do is I'm going to find ZT, and then I'm going to say that the complex power is the voltage source squared divided by ZT. So that's how I'm going to find the hypotenuse of our power triangle. But before I can do that, like I said, I need to find ZT here. Well, Z for load 1 is going to be 25 ohms at an angle of minus 31.78 degrees. And that's going to be in parallel with 15 ohms at an angle of 53.13 degrees. So I'm going to have to do product over sum here. So I'm going to have to say this times this divided by this plus this. So I'll write that here like this. Z1 times Z2 divided by Z1 plus Z2 equals ZT. And the rest of it I'm going to do on the calculator. So let me do it. So we've got 25 at an angle of minus 31.78 degrees times 15 at an angle of 53.13 degrees. So there's that, divided by 25 at an angle of minus 31.78 plus 15 at an angle of 53.13, close parentheses, and that gives me 12.38 ohms at an angle of 23.55 degrees. Okay, so this is ZT. Well, now we can figure out what the complex power is. It's going to be 220 volts at 0 degrees squared divided by 12.38 ohms at an angle of 23.55. All right. So give me 1 second here and I will calculate that. So 220 at an angle of 0, and we are going to square that. There's that. Divided by 12.38 at an angle of 23.55 degrees. All right. So I am getting 3.909 kilovolt amps. So I'm just going to call that 3909 volt amps right there. And let's draw that triangle. This is the power triangle right here. So the apparent power is just going to be this right here. So that's 3909 volt amps. So the apparent power is just the magnitude of the complex power right there. And what's the angle of the power triangle going to be? Well, it's going to be the same angle as the total impedance, which was 23.55. Okay. Well, how do we get the true power? So that's the power that's doing all the work in this circuit. And that is this portion of the triangle. Well, that's going to be the apparent power times cosine of that angle. So 3909 cosine of 23.55 gives us 3583. And that is in watts because it's true power. And then we're going to do the same thing for the reactive power. And so that is 1561. Let me turn my paper here. 1561, and that is volt amps reactive right there. So this is our power triangle right there. We have done it. We have found the apparent power, the true power, and the reactive power for this circuit, and we have solved for the component values in these two loads right here. So that about does it for this video.